going to start this quick recording with just sort of refreshing ourselves with what we did last week and what we've done kind of leading up to this assignment midweek in week 2. Last week, what we thought about was where do lines cross? And remember that we looked at systems that way. We thought about the beginning of the story, we talked about the rates of change, we talked about where those lines cross. And so I just want to remind you that whenever we have a system of linear equations, what we're really talking about is on the graph, where do those two lines intersect? And so we have this example here, and it says y equals -1/2 x plus 3, and then we have another line, y equals -3 over 6 x minus 1, and the question is, where will these two lines intersect? Now, for some of you, you may notice already that there's something kind of funny about this. I think some of you may notice that 3 over 6 is easy to simplify. That's 3 out of 6 is 1/2. And so really we could rewrite this equation. We could simplify this second equation and say, oh, well, this is just y equals -1/2 x minus 1. And then we start thinking, okay, well, so I know that the whole reason that we're thinking about equations in this way, and we've been working on this through the beginning of this week, is that we know that these both are in y equals form, and specifically, they're in a very important y equals form. They're in y equals slope times x plus the y-intercept form. And so this number that's with the x in both of these equations, I'm going to go ahead and circle this because we're going to really focus on this. This number is our slope. This number is our slope. Each of these lines has a slope of -1/2. And so just intuitively, what we're really thinking about here is two lines that essentially have the same angle. They go down at an angle of over by 1, down by 2. So we're talking about, down by 1, over by 2. Rise down is 1, -1, run is 2. So down by 1, over by 2. We'll see that in a moment because I'm going to graph these. But the main thing that we have to notice is that since those numbers are the same, what we're talking about is that their steepness, the way they're sort of angled, is the same. And if you do this with your hands, you can think, oh, wait a second, if they're at the same angle, where are they ever going to cross? These are parallel lines. And so, indeed, when we get an equation where the two slopes are the same, what we've got is a special situation. These lines, they're not going to cross. These particular lines are not going to cross. And so just revealing this, and you can do this as a way to test for yourself. I went ahead into Desmos, into the graphing calculator, and I just graphed those two equations. You can see those lines are perfectly parallel. These lines are never going to cross. And so if we say, hey, the solution to a system is the place where two lines intersect, then there's just not going to be a solution. And so, in fact, when we get a problem where those slopes are the same, one possibility here is, well, these are parallel lines. This has no solutions. And indeed, if you get a problem like this on a test, this really is the right answer to put down. These have no solution because they have the same rate and they are parallel. In this next example, you'll see another situation where two lines are given that have the same slope, but we actually get a slightly different result than what we got in the first example. So here I've got y equals -1/2 x plus 3. That's the equation we started the first example with. And then I chose this second equation, so y equals -6/12 x plus 3. Now, as we did in the first example, we might notice that this fraction is actually just not a simplified version of -1/2. 6 out of 12 is really 1/2. And so when we go and we write that as that equivalent, -1/2 x plus 3, what we see when we look at this equation after it's been sort of simplified is that I've got a line, y equals negative 1/2 x plus 3. It's got a slope of negative 1/2. It's got a y-intercept of 3. And then I've got this second equation that when I first looked at it, looked like another line. And so I might have been able to graph those two lines and see where they cross. But then I noticed that they have that same slope. But the other thing that they have in common is that they actually have the same y-intercept. Essentially, these two lines are the same line. So if I were to graph those two lines, what you would see is both of those two lines are right there on top of each other. Now, it's a little bit hard to see. I made this first graph have a sort of a dotted red line, and you can see if you look real close that the black line that represents this other equation is really right on top of it. So what we say here is that these two lines are actually on top of each other all the time. So there are an infinite number of points that are essentially at an intersection point. You know, we have two lines that cross like this. They only cross in one place. If I've got two parallel lines, they don't cross at all. Well, these lines are concurrent is the word that we use. These two lines are directly on top of each other. So this system, if we were to get a system like this, and we would see that they have the same slope and the same y-intercept, so same slope, negative 1/2, same y-intercept, positive 3, we would say that this has an infinite number of solutions. And again, we would have to do no solving to do that. We would just be looking at those equations and thinking about them as lines. Now, before I go away from this example, I want to show you the way that it really shows up more likely. And that is that you might have this second equation sort of disguised a little bit more. Now, I already tried to disguise it by making it 6 out of 12, which you guys quickly saw was 1/2. But sometimes what will happen is we'll get an equation that is not in y equals form, not in slope-intercept form, and you might get something that looks, let's say, a little bit like that. So this is really that exact same equation, which is really the same equation, y equals negative 1/2 x plus 3. But in order to really get that so that you can see that those are actually just equivalent equations, you would have to solve this to get y by itself. You would have to put it into slope-intercept form. So if we were to then add 3 to both sides of this equation, so that we would eliminate that 3 term there, what we would have is y equals negative 6/12 x plus 3. And so now we're sort of right back to where we started. We would see this was 1/2, and we would say, oh, those are equivalent. Same slopes, same y-intercepts, infinite number of solutions. For this last example, I want to show you a more typical system that falls into this sort of special category. I've got 2x plus y equals 2, and then I've got y equals negative 2x plus 2. Now, if you're familiar with substitution method, you might start right in and start solving this, and you would substitute this negative 2x plus 2 in here for y, and then combine like terms and solve. And certainly you can approach this problem in that way. What I want to show you is that if you look at each line and think about them as graphed lines, you can actually save yourself a lot of trouble with a problem like this. So we know that what we really like to see is y equals form. We like to see that slope-intercept form. So this second equation is already in slope-intercept form. It has a slope of negative 2. It has a y-intercept of positive 2. And I'm going to leave that alone. I know some stuff about that line. Next, what I'm going to do is I'm going to take this first equation. I'm just going to rewrite it so that I can mess around with it. I'm going to give myself some space to work. And I'm going to try to get y by itself. So right now, y is on this left-hand side, it is being increased by 2x. So I'm going to go ahead and do the opposite of adding 2x. I'm going to subtract 2x from both sides. This way I can get that 2x term to be eliminated. And what I have here is y equals negative 2x plus 2. Now I could have written 2 minus 2x. That would be the same thing. I put it in this order because we're real familiar with slope here of negative 2. That's the coefficient of that x term. And y-intercept of 2 here. So when we take this first equation and just put it into a form that is easy to recognize, this turns out to be the same case as the second example that I showed you in the video, which is same slope, same y-intercept. These are essentially the same line, and so this has an infinite number of solutions. And that's as far as we would have to go with that problem. We showed you an example where a system had no solutions. We showed you an example where a system had an infinite number of solutions. I thought I would finish with one that actually does have one solution. But I want to just sort of attack it in a different sort of a way. I just want to use the same thinking that we did on those other examples to see here that when I see this system and I look at it and I say, well, this equation y equals negative 3x plus 2 has a slope of negative 3 and a y-intercept of 2. And this has a slope of 2 and a y-intercept of 8. What I know about these two lines is that because they are at different angles, essentially, those slopes, one has a negative slope, one has a positive slope. If those numbers are not the same, if those slope numbers are not the same, we know there's going to be one solution. When you have two lines, if they're at different angles, if we keep following those lines, they will eventually cross. And so that point will be our point of intersection. That will be our solution to the system. So to recap all of the examples, if we look at the slopes and the y-intercepts of the two equations that were given, if the slopes are the same, but the y-intercepts are different, this is the case where we have parallel lines. They're not the same line, but they have that same angle because they have the same slope. This would have no solutions. If they have the same slope and the same y-intercept, well, we're talking about the same equation. Those cross everywhere. They're directly on top of each other. This has an infinite number of solutions. And finally, if we have different slopes, and it doesn't matter whether they have the same or different y-intercept. We don't even have to look at it. If they have a different slope, this will have one solution.